A relation is a set or a collection of ordered pairs. That's really all it is. Nothing more than that. So we could, as an example, have exactly that, just a set of ordered pairs. So we could take -1, 3. We could take 3, 4, 5, 3, -1, -2, and 0, 6. So these 5 ordered pairs, these 5 points, can make up a relation. Okay, and really a relation is just how two different things relate to each other. How this x relates to that y. There's some kind of connection. We don't know what it is. It could be from a formula. It could be from something else. I don't know, but it's just how they relate. We could also see relations that are made up of not a finite number of points, but an infinite number of points. So something kind of like this. Okay. This is a relation. It is made up of an infinite number of points, an infinite number of ordered pairs in order to make up that picture. Okay. When we talk about relations, we also want to talk about domain and range. So, for those of you that are in my class, you know that this is going to be a topic that's going to be on your next exam. So the domain is the set. It's the set of x values used in the relation. The set of x values used in the relation. And then on the flip side of that, we talk about the range. And the range is the set of y values used in the relation. All right, so if we were to look up here for this first example, we want to talk about what is the domain. The domain is going to be the set of all x values that we see. Now, I like to put these guys in order from least to greatest. So, we see that for the x's, we're using, -1, 3, 5, -1, 0. So, -1 is the one furthest on the left. Then we have 0. And then we have 3 and 5 as we put these guys in order. Now, you might say, what if one of those values is repeated? It doesn't matter if a value is repeated. When we're trying to identify the domain and range, all that matters is, are we including every value that's being used? And yes, it doesn't matter how many times it's being used, just the fact that it's being used is enough for its inclusion. And if I look at the range here, the range is going to be the set of y values. And again, I like to put these guys in order. So let's see, the lowest y value is -2, and then 3, 4, and 6. So that's your domain and that's your range. Here, when you have a finite set of points, you're just going to pick off those x coordinates for the domain, pick off the y coordinates for the range. And again, I like to order mine, but sometimes, like if you're doing homework in my math lab, they don't really care about the order. For this picture right here, the domain is the set of x values, and you see that as we go from left to right, there are an infinite number of values that we're using. And when we talk about the domain, it's not where it is across the x-axis, but that's not what we care about. We care about the x values that are used to make up this picture. And so for this one, this is going to be all real numbers as we go all the way left and all the way to the right. So using that same interval notation that we used for talking about solution sets for inequalities. This guy goes all the way left, goes all the way right. There are no gaps, there are no jumps, there are no spaces, all real numbers. For your range, when you're talking about range, you're talking about how your y values operate. And that's going to be as you go from bottom to top. So domain is left to right, range is bottom to top. So this guy's going all the way down, and as you trace along here, it goes up, he comes down, but then at the end, he is going up forever and ever. So that means he's also going to be all real numbers for the range. All right? So that's what it means to be a relation. That's how we identify the domain and range. We have some examples here to work through here in just a moment. More pictures, more elaborate pictures for us to identify the domain and range. But before we do that, we need to talk about what it means to be a function. And a function is a relation. A function is a relation where each x value is paired with only one y value. Okay? So, good afternoon to you. So here's the thing about being a function. There are a lot of real-world examples for being a function. Okay? Our x values are oftentimes what we refer to as the inputs. Okay? And the y value is the output. Okay? So you plug in one number, you get out one number. That's the way that it's supposed to be. We see this happening with vending machines, right? You press one certain button combination, you get out one item. You don't get out multiple items, okay? Punch in one thing, you get out one thing. On my calculator, wherever that goes, where'd it go? On my calculator, if I type in something and I hit enter, I should get one answer. One input, one output. That's what it means to be a function. So what we want to do is we want to look at the examples that we gave above and determine whether or not these guys are functions. So if you look at this first one in terms of the ordered pairs, does each input give you one output and one output only? And you might say, well, yeah, until you realize what's going on here with -1. See, -1 is matched up with 3. So that means you press -1 on your function machine, supposedly function machine, and you're going to get out the number 3. But then you realize that over here, -1 also gives you -2. Well, it's not supposed to work that way in order to be a function. You plug in one number, you get out one number. That's it, no more. So up here, this is not a function. It's still a relation, but it's not a function. Here's another example. You could have the x-coordinates being people, right? And the y-coordinate could be their birthday. Well, if that's the case, that should be a function. I have one birthday. My wife has one birthday. My sons have one birthday. Now, does that mean that they are the only people who have that birthday? No, right? My brother-in-law has the same birthday as me. Okay? So my birthday is not unique. Like, I'm not the only person who has that, but I only have one birthday, right? I, as the input, will have one birthday. Now, some of you may say, well, what about here? The 3, like 5 goes to 3, -1 goes to 3. Well, that can happen. Think about vending machines. You know that sometimes they might have, like if we're talking about a soda machine, there might be more than one button that you can press to still get your particular soda, if you want to get a Sprite or whatever, right? I could press this button or I could press that button and it still gives me the same drink. But when I press that button, I'm still only getting one output. That's what it means to be a function. One input, you get one output. What about this wavy guy right here? Is he a function? Well, we don't have the list of ordered pairs so that we can one by one go through and see if it's a function or not. So we have this neat little test called the vertical line test. And I'm sure you guys remember that. It's nice and easy. So the vertical line test. Okay, and this says that for a graph, to represent a function, every vertical line must cross it in at most one point. So when you look at a graph, every vertical line can only cross it in at most one point. So if you have a straight edge, like a ruler, and you just work your way across here, does this ruler, when it's oriented vertically, does this ruler ever hit more than one point as I trace along that curve? And you see that it never does. No matter where I draw a vertical line, whether it's here, it only hits it one time. If I draw a vertical line here, it only crosses the graph in one spot. If I draw it here, or here, anywhere, you see that I'm only hitting that graph in at most one spot. An easy check here is if you ever see your graph curve back on itself, if you ever see it kind of stacked on top of itself, it's going to fail the vertical line test. Other than that, we should be okay. So, now that we kind of have this in our minds, and we see here that this guy, this one right here, is a function. Let's run through some examples, and let's see if we can identify if the graph is that of a function. Oh, I really got to change that. So we're going to see if what we have here is really a function or not, and then we're going to determine the domain and range. So, just now realizing that what I printed front and back, and I've got to change the settings on that printer. All right, so here is our first example. You know what? That's going to bother me. You guys give me just a second. Now, you know what? Whatever. We're just going to make it work. Or is that too distracting? Give me a second. All right. Yeah. Okay, well, I'm glad you thought it was okay. It was too much for me. I was about to lose my mind. So now the graphs are going to look even better. See, now you don't have the other stuff getting in the way. All right. So for this picture right here, does this picture represent a function? Okay. So when you look at it and you take your vertical line, you try to pass it along here, is it going to be a function? So you see immediately that we're in trouble, right? So if we take this and we try to draw a vertical line, you are crossing this in two different spots. So right, Kevin, not a function. Now, even though we say that this guy is not a function, we can still talk about the domain and range. So your domain is supposed to be the set of x values, and this is where we can easily get lost if we're not paying attention. So the x values, as we go from left to right, let's see what we are including. This graph does not start until right here when x equals -8. do not get caught up in where the graph crosses the x-axis, because I don't care. I care about the x values that I'm using, and I start using them right here at -8. So what we can do is that we see that we're starting here at -8, so I sometimes like to draw on the number line. And you start at -8, and this guy just goes over to the right, and it stops right here at an x value of -2. So the domain is bracket from -8 to -2, like that. And then we want to switch gears and talk about what is the range. So the range is going to be bottom to top. So as you see, you maybe take a ruler, slide it up here. We have nothing until we get to a y value right here of -3. So we are including -3, and this goes all the way up. And you see it doesn't stop until I get up here to a y value of 7. I don't go beyond 7. I don't go below -3. So if we were to map all of that onto that y-axis, it's going from -3 up to 7. So that's how you do the domain and range. Right? Think about it as we were taking our ruler here. We have nothing until we get to an x value of -8. And so from -8, we have a picture. We have a picture until we get to -2, and that's where we stop. So from -8 to -2 for the domain, from -3 up to +7 for the range. And that's how we do it. It doesn't need to be complicated because it's not complicated. So let's look at this guy right here. Mr. Wavy Guy. Okay. Does he represent a function? Well, if you're not sure, take your ruler and slide it along. If at any point you see this ruler going through more than one point, then it's not going to be a function. As we keep going, I don't think there's any problem here whatsoever, right? I don't ever see my graph curve back onto itself. And in the last problem, that's what I saw. I saw this guy start here, and he curves back onto himself. And I said, if you see that, not a function. So yes, as you say in the chat, this is a function. So yes, it's a function. My domain. All right, let's try to describe the domain as I go from left to right. Notice as I go from left to right, even though it's got all these hills and valleys, I don't see any gaps or any breaks. So if we can take this graph at its word, that's going to keep going left and right in that same pattern, then my domain should be all real numbers. Right? It's going all the way left, all the way right. And what about the range? Let's see. If I take my ruler, I have nothing until I get to a y value right here of -1. So the lowest it gets is -1. And how high does this guy get? If we keep sliding up here, we see the highest this guy gets, and it's pretty consistent. It stops up here at 5. Now, I know that we did an example in class where we had one guy that kept going back and forth, but the oscillations kept getting wider and wider as we did that. But this one isn't. This one is staying very, very well contained in between, as you guys are seeing, between -1 and 5. Now, you forgot something there. You didn't tell me what we're going to have on the ends. These guys should both be brackets, right? So bracket -1 to 5. Doesn't seem to be too bad, right? Cool. All right. Oh, this one's so fun. So let's take this guy, this vertical line. Is this a function, yes or no? Let's see. For the two people who are watching, both get the right answer. Come on, you got this. take a drink while you're thinking? Oh yeah, one vote for no. And that is correct. This guy is so not a function. And you might say, why not? Well, let's slide your vertical line here. I'm fine, I'm totally fine until I get right here, and then I am hitting this guy in an infinite number of points. So this guy fails the vertical line test. The vertical line fails the vertical line test. Now let's talk about what the domain is. The domain can be tricky. Remember, the domain is the set of x values that we use to form this picture. And as you see, I'm not going to the left, I'm not going to the right, I am only using an x value of 4. So we don't use interval notation for this. The way we have to express this, though, is we've got to use the curly brackets, the set builder notation, where we say this, using those curly brackets. So if you have to do this in my math lab and you're trying to find those characters, oh good, I was about to say, you just have to do shift bracket on the keyboard, and that's going to give you the little curly brackets. So it's just for this when we use, like on the very beginning of the notes, and we had this guy right here. When we were talking about the domain and range for this, we used the set builder notation because we were just listing those elements because we could do that. They were discrete. It was just those 4 numbers or those 5 numbers or whatever. When it's a range of values like this, we use interval notation. All right, so the domain is 4, and now we need to talk about the range. Remember, the range goes from bottom to top. So from the bottom, we're already starting here. Like this guy's going off the page, right? And as we go from bottom to top, there are no gaps, no breaks, no spaces. So my range is going to be all real numbers. Ba-da-ba-da! Right? So easy. So easy. For those of you that are in the stream that are my students, I know that 2 of you are at least, stick around after I wrap up this lesson because I can give you a little heads up to some of the stuff that you guys can see for next week. Kind of excited for it. Hope that it works out for you guys because I'm actually changing the way I was going to do it because I found an easier way for you and for me. Oh, somebody made a mistake here. What is this junk? Maybe, did I print something wrong? All right, what do you think? Function, yes or no? Yeah, this is kind of obvious that this is not a function. If we try to slide a vertical line, we're fine, and then we just start hitting this guy in an infinite number of points. So this is not a function. But again, that doesn't mean that we exclude the discussion about domain and range. So the domain is what? Now remember, domain is bouncing, it's got to go from left to right. Yes, Lydia, again, not a function. So from left to right, what do we have? Well, if you slide the ruler, you have nothing until x gets right up here to -1, and then we go all the way to the right, and then we top out right here when x is 7. And so we can see that our entire picture is bounded between -1 and +7. Yes, Kevin, with the correct notation using those brackets. So that's bracket -1 to +7, just like that. Now the range. Well, the range, as we've mentioned, goes from bottom to top. And even though this guy like slithers back and forth, from bottom to top, there are no gaps. There are no jumps for this guy. So his range is all real numbers, right? So you can either write all real numbers, you can write -infinity to infinity, you can also use the symbol that we use for all real numbers, which is that funny looking R. And depending on what textbook you have, it may show up a little bit differently. All right, so not too bad. All right. I want to save that one. let's do this. All right. Let's see. Function, yes or no? Does this graph curve back on itself? Or, as I go from left to right, is he okay? And you see, he never curves back on himself. If I take this vertical line and I start passing it through here, everything is fine all the way across. So yes. Yes, this is a function. What about the domain? Right? The domain is supposed to be the set of all of the x values that we're using. So, from left to right, now see, this is where things get kind of weird and difficult here. This looks like this guy is going straight down, but he's not. He's actually going out to the left forever and ever. So your domain would be from negative infinity to infinity. We just run into this issue where on the sides, on the ends, this guy gets really, really steep. And since he's getting steep, we think that, oh, he's not going out all the way to the left and to the right. It's just that we have a very limited view of this function. And then what about our range? Our range is as we move from bottom to top. From bottom to top, this guy goes up, he comes back down, but he goes up at the very end. If you were to try to graph this and plot it on the y-axis, he's going down, he goes up, he comes back down, and then he goes up at the very end. So, the range is still all real numbers, right? It's almost too easy, right? Just, God, so good. Until I go and I mess things up. Now, if this graph had been oriented this way, I hope that we could see that the domain and the range would still be the same. However, this would no longer be a function, right? Because you would totally fail the vertical line test. And it's just a simple manipulation that I can do in my graphing software to turn it sideways to make it not a function. So who knows what you're going to see on your test. All right, I think this is the next one I want to do. Now for this one, it's understood that here on the left, he's going out forever and ever. So let's see, is this a function, yes or no? And if you ever tell me that something is not a function, that means that you can draw a vertical line, and that vertical line is going to go through more than one point. So what do you guys think? Function, yes or no? One vote for yes. The only spot here that is even questionable is going to be right here. But again, we have to understand that we are trying to take something that's dealing with an infinite number of points, and we're trying to put it to something that's made up of a bunch of squares, pixels. And whenever we graph it, we're just doing our best. Right, so it looks like it might be failing it right here, but it's not. It's fine all the way. So yes, this is a function. And you already know the question I'm going to ask you next, so you can go ahead and be typing your answer. So if I ask you, what is the domain? Well, as we go from left to right, if I put my ruler here and I try to see, oh, this guy's going off to the grid, off to the races here to the left. And he is still here. He's present up until right here at 4. And this is where he stops. So as you slide from left to right, picture, 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 and then we stop. So my domain is from negative infinity up to 4 with a bracket. Right. What about the range? And again, a lot of times it's a matter of perspective that can throw us off. Our range, let's see what this guy's doing. He's going down and to the left. However, he's going down forever and ever. So this guy is coming from negative infinity. And even though we don't see it over here, we don't see it on this bottom of the graph, we are assuming that this guy's going to keep going down. So from negative infinity, he keeps going up and up and up until he gets to that y value of 5, right? So your range is from negative infinity to positive 5. Yeah. Right? Take that. All right, we got one last guy here before I kind of switch gears. And we have this one. Is it a function, yes or no? No, not a function. Right. Now this is made up of, it's got two different pieces here, but as I slide my vertical line here, you see it fails the vertical line test. All right, so let's talk about the domain. So as I slide my ruler along, I have nothing until I get to an x value here at 1. That's where both of these pieces start, and both of these guys go on forever and ever out to the right. Now you could say this piece goes from 1 to infinity, and that piece also goes from 1 to infinity. It doesn't really matter, because once you put those guys together, it's still that section that is just from 1 to infinity. What about the range, though? The range is going to have a fun little element to it, right? So notice here, as I come from the bottom, this guy, again, we are assuming this guy's going to go down and down and down forever and ever, right? So we're coming from negative infinity, and we trace along here, right? Keep going up and up. But when we get to negative 1, this guy stops. And then there's this gap, and there's nothing here until we get to a y value of 6. And then this guy goes on and on forever after that. So once we have this mapped to the y-axis, we now have to translate this into our interval notation. Interval notation goes least to greatest, left to right if you're doing domain, but bottom to top if you're doing range. So from the bottom, negative infinity up to negative 1 bracket. Right, so the range will be a union because we have two disconnected pieces. So that means we're going to go union and pick back up here from 6 to infinity. Now, where is it? Let me give you guys a little bonus here, okay? So I'm going to draw a new picture, and we're going to talk about what will be the domain and range of this. And this is going to connect with some of the first videos that you see once we come back from our break. Okay, I'm going to do this guy. All right. All right, so let's take a look at this picture. I know this one looks a little bit smaller than the others. It's just what I had on hand right now. Is this a function, yes or no? For a picture, all that we have to be able to determine is, does it pass the vertical line test? And we see here that it is, right? As I slide my vertical line across, it's going to pass the vertical line test. Let's talk about the domain. So my domain, as I go from left to right, so I've got this guy almost looks like a parabola, right? And so it looks like he's got to keep going out to the left. So if I were to graph this guy onto the number line, onto the x-axis, that's from negative infinity. He's going up until negative 2. Now notice something here. At this point, that's an open point, an open circle. If I were to do that here on the number line, like that, we know that from our experiences with solving inequalities, we know that that point would not be included, which is then going to correspond to parentheses. We have a gap where there's nothing here, and we come back here when x equals 2. That's fill it in, right? This is a filled in point. So this is now going to be filled in, and this graph is continuing on to the right forever and ever. So since we have this gap, we have to use a union. So this is going from negative infinity to negative 2, union, and then we pick back up here, bracket to infinity. And it's very important that we understand that we have the bracket there. We have a bracket here because we're including that point. We have an open circle, so that means parentheses there. Okay? Does that make sense? Are you guys okay with that? I hope that you see that once you put it onto the x-axis or for the y-axis, that it's very easy to see what the domain or the range will be. Now, your range. So we can do this in two different pieces. If I start here with the guy that's on the left, he is an open circle at 2. He goes down to 1, and then he bounces up to infinity. So this section right here would be the range for that little partial parabola. Here, this guy starts here at negative 3, and he goes all the way up. So when we talk about the range, there's no gap here, right? Even though we have two different sections, two different pieces of this function, my range doesn't have a gap like I have for my domain. So my range is going to be from negative 3 to infinity, right? Now, if you were to say this, if you were to say, Mr. Craig, what if I say that this is from 1 to infinity for that parabola guy, union, and then you do negative 3 to infinity? Well, the problem with saying this is that it's work that's not done, because all of this right here can be simply written like that because there's no gap. The only time we need to leave a union in our interval notation is if there's a gap, if there's a jump like I have here for the domain that you see in red. Otherwise, you just write what you see. Because this 1 to infinity is actually a subset of this larger section from negative 3 to infinity, so you don't need to say it twice. Okay? So there you go. There's your crash course review in domain, in range, and whether or not something is a function. All right? Now, I want to make sure that we kind of get a head start on the stuff that we're going to be seeing tomorrow, or that we're going to be reviewing tomorrow, and that's just function notation, right? So in the past, we would have done something like this. Y is equal to 5x plus 8. And if I say complete the ordered pair, if I say complete this, complete the ordered pair 4, comma, something. And if you saw this in my math lab and it said, what's the other part of the ordered pair? You know that means you are given x and you need to find the y. And so you would say y equals 5, replace the x with 4, plus 8, y equals 20 plus 8, which gives us 28. So that's you completing the ordered pair. So instead of saying y, we go into this function notation. And you know that once we go here, we rarely ever leave this. I was making more videos for you guys just before this stream, and a lot of function stuff going on. But really, make sure you understand that when you're talking about functions, understand where the emphasis is. So we go from saying y equals 5x plus 8, and we make the transition now, and we say f of x. So f of x equals 5x plus 8. So it goes back to the whole concept that we had about functions at the beginning of today's stream. where we said one input gives you one output. And that's kind of what we're used to seeing. So here, you're going to see words like this that say evaluate f of 4. And what that means is to identify the function called called f right here, and instead of writing x, you're going to write 4. It's just making a substitution. And so the correct way that we write this and we show our work is that f of 4 equals 5, use parentheses for any place where you had your variable, and then you plug in that input value. Okay? That's what it means to evaluate a function. We do the math, and we come up with 28. Right? Plug in a number, you get out one number. That's what it means to be a function. One input gives you one output. Okay? And so really the big idea about functions is, can you replace x and follow the order of operations? So if you were given that f of x is equal to x squared minus 3x plus 9, and you need to evaluate, or sometimes they use the word find, evaluate f of negative 7. Okay? All that is saying is to take this function, and any place you see x, remove it. Take the x, take it out, and you're going to plug in negative 7. So your work is going to look like this. Replace the x's with parentheses. So let's do that. I'm going to circle the x's so we know where they are. I'm going to replace all of those guys with parentheses, but I'm going to keep everything else. I'm going to keep the square. I'm going to keep that coefficient of 3. And now, inside of these guys, I'm going to plug in the input value, negative 7. If you understand that concept, then the rest of this, the rest of evaluating functions, is just, can you do the order of operations? That's all I'm asking. So, order of operations would say, to do the powers first, so that gives you a positive 49. Then multiply. Well, there wasn't anything in front of this, so we can just say 49. Negative 3 times negative 7 is positive 21. And then plus 9. So 49 and 21 is 70, plus 9, and we get 79. Please make sure you understand that what's going on here is not solving. We are not solving anything. We are plugging in a number and we are evaluating. That's it. So in terms of understanding this on a deeper level, understand that you plugged in negative 7 into the function and you got 79. That's the same thing as us looking at the ordered pair, negative 7, comma 79. You plug in x, you get out y, and y is your function value. That's all there is. There is really nothing more to it. The only time you use that negative 7 is that you just plug it in. You replace the x's with negative 7, and you do the math. That's really it. We shouldn't make it any more complicated than that. Now, a lot of times we use f of x, but sometimes we use g. So I can say g of x is equal to negative 9x plus 2. And I could say find or evaluate g of 300. And all that means for us is that we take this function and we replace the x's with parentheses and we plug in the input value in place for x, like that. So we have negative 2700, right? Because that's just negative 27, add on the 2 zeros, plus 2. And altogether that's negative 2,600 98. Right? So, again, hoping that that's nothing too terribly crazy. Let's see some, some odd kind of examples that you might see in the homework. All right, so if you are given f of x is equal to 7x plus 4, and you need to find f of m. No matter what you see in the parentheses, it works the same as any other function evaluation. You take your function as it is, you replace the variable with parentheses, and you fill in the parentheses with this input value right here. In this case, it's just another variable, m. And we are left with 7m plus 4. And we can't do anything with that because these guys are not like terms. And so yes, sometimes with functions, we are plugging in other functions. If I say, let's plug in 8x minus 7. So now it's 7 parentheses plus 4, just like it was before. But instead of plugging in m or x or a number, we're plugging in the variable expression 8x minus 7. Well, we can't leave it like this. We actually have to work that out. So we distribute. 7 times 8x is 56x. 7 times negative 7 is negative 49. Plus 4. And we can simplify this to 56x minus 45 when we combine like terms. So again, that's hopefully not too bad. I know that you would rather be plugging in regular numbers, but this is what we have. Now let's make things a little bit crazier. Suppose g of x is equal to 3x squared plus 5x minus 12. And you need to find g of x minus 5. Alright, so the big picture here is understanding how functions work. When I say find g of x minus 5, it's like saying find g of 3, find g of negative 2. You take all of these x's right here, and you're going to replace them with x minus 5. And as we were showing already, first of all, you start by rewriting this so that you don't have x, but instead you use parentheses. Anytime you're substituting, use parentheses. That way you don't make silly mistakes when it comes to your signs. So here's the basic framework. We replaced the x's with parentheses. We kept all of the other symbols intact. We kept the coefficients, positive and negatives. We kept the powers too. But now we're going to plug in x minus 5 into this. Like that. Alright, so following the order of operations as best we can, we know that powers need to happen first. The 3 is still there. Please don't let the 3 sneak in. The square is only applied to x minus 5, just like up here. The square is only connected to the x, not the 3. When I square x minus 5, you can use the shortcut, or if you want to, you can go up to the side, take a little scrap piece of paper, and work out the product of x minus 5 times x minus 5. So we work this out, x squared minus 5x when I start to FOIL. Then distribute the negative 5, so that's negative 5x plus 25, and all together, that's x squared minus 10x plus 25. We also have a little shortcut for that, though. We've done this before. So x squared minus 10x plus 25, and just bring down the rest of this. And from here on out, it's really just working with polynomials. Can you distribute? Can you combine like terms? So here, let's distribute the 3. All right, so we have 3x squared minus 30x plus 75, and then distribute the 5. So we get plus 5x minus 25, and then we'll bring down the minus 12. And we just need to combine like terms at this point. We have 3x squared, that's the only x squared term that we have. We have negative 30x plus 5x, so that's negative 25x. 75 minus 25 is 50, and 50 minus 12 is plus 38. So you plugged a variable expression in, and we got a variable expression out. That seems to be the way things go. I know it's not just a number for you, but that's what it looks like when you plug a function, or when you plug a variable expression into another variable expression. All right, so tomorrow we're going to be looking at function operations, function composition, and there will probably be time for us to kind of do a recap of the parent functions so that on Friday we can focus strictly on graphing non-linear functions.